Hello and welcome to this lesson on the motor effect. This is your second chapter of electromagnetism. So as the name suggests, the motor effect. What is motor? Motor comes from the term motion, right? You have motion when you have force. So the motor effect in this chapter will be learning about force. How is this force created? When you have magnetic field and current present together in the same space, force is produced. This is the second chapter of electromagnetism. I believe you all would have already seen the lesson 1, which lays the foundation for the second chapter. Now, some highlights of this chapter. This chapter talks about two very important, very well-known concepts. These are your Fleming's left-hand rule and the kicking wire experiment. So in this chapter, we'll be covering these two concepts as well. Right? So let's start with this chapter. Now let's understand the setup which is shown on the screen. You see a setup here, right? Focus on the setup. What do you see in this setup? You see a horseshoe magnet with its two poles, north and the south pole, and in between these two poles you have a wire passing through, right? So what is there in the setup? You place a copper wire as is shown here. When the current is passed in the wire, it experiences a force. Why? Now this is a question that I want you all to think about. You have a magnet. In between you have a wire which is carrying a current. As long as there is current in the wire, there will be a force produced. So why is this force produced? Think about it for a while. Pause the video if you want to, and then get back and start the video again. Otherwise, I'll give you a hint as well. Suppose that you have a bar magnet, another bar magnet, right? These two are magnets. Whenever there are two magnets close by, what happens? There is a force between the two magnets. The force can be a force of attraction. The force can be a force of repulsion. Attraction and repulsion both are forces, right? It can be attraction, it can be repulsion, doesn't matter. Both are forces, right? If like poles are present close together, there will be repulsion, which is a force. If unlike poles are facing each other, there will be a force of attraction, right? But again, there will be a force. Important thing to understand, whenever two magnets are close together, there will be a force present. So apply your understanding of this particular thing which I just spoke about to understand what's happening in this picture here. Why is there a force produced? All right, if you have understood lesson 1 well enough, you would understand that whenever there is current in a wire, it behaves like a magnet. It produces its own magnetic field. So this wire which is present in the cap here, it has now started acting like a magnet. So this whole picture, whole scenario can be imagined as if there are two magnets close together. So you have one horseshoe magnet and then this wire magnet. So whenever two magnets are there present together, what do you see? You see a force being present, right? And this is exactly which answers this question. Why is force produced? So why is the force produced? The wire here, the wire produces its own magnetic field. And we already know that two magnetic fields always have a force. Now this force can be a repulsive force or it can be an attraction force due to interaction between their magnetic field lines. Right? So what do we understand from this particular topic? We understand that whenever there is a current flowing in a conductor, and if that conductor is placed in a magnetic field, there will be a force produced. All right, so let's proceed. If it is a force, it has to have a direction. Force is a vector. If it is a vector quantity that we are talking about, we need to think about its direction as well, right? So how do we find the direction of the force? We find the direction of the force using the Fleming's left hand rule. Again, here you have to be careful that you are using the left hand to find the direction of the force. So take out your left hand. How would you use your left hand? Open the first three fingers of your left hand such that all the three fingers are perpendicular to each other. If you see, that's how you have to hold your fingers. The angle between all the three fingers is 90 degrees. Alright, so what you have to do? The first finger always points in the direction of the field. F for first, F for field. First finger in the direction of the field. The second, the C in the second determines the current. This is your second finger, it gives you the current. And the thumb, TH, in the thumb gives you the thrust. Thrust is a force, right? So that's how you remember. TH in the thumb gives you the thrust. Second finger with second term carries a C, which gives you the current. The first finger, which carries a F, gives you the field. Right? So that's how you use your Fleming's left hand rule to find the direction of the force. So let's find the direction of the force in this particular picture. How do you determine the direction of the field? The field always is pointed from the north towards the south. So this finger will point north to south. Alright. Current is given by the second finger. So current, if you see, it's coming out this way. So place your second finger in the direction of the current. The thumb goes up. That means your force, which is experienced by this conductor or this wire, is in the upward direction. Alright, this is your Fleming's left hand rule. Very simple to understand, very simple to remember as well. If you remember all these hints which comes from the name of the fingers itself. Alright, so let's answer a few questions. What is the direction of the force when the current is reversed? Let's reverse the current. Let's change the marking of the current on our diagram. The current is reversed. Maybe it's because the battery is now reversed. Now you have the negative terminal on this side and positive terminal on the other side, right? The current is flowing the other way around. Let's use the Fleming's left hand rule. The first finger points in the direction of the field, north to south. The second finger points in the direction of the current, right? So please do remember, because of this recording, there is a lateral inversion. The fingers might not look like as you see on the screen. So when you do it correctly, you should get the correct force. That's what is more important. So practice it yourself and see. You should find out that the direction of the force reverses, right? You'll see that the new direction of the force is the opposite. So what happens when the current is reversed? What did you find out yourself? You found out that the force is reversed. Okay, so let's answer this other question, which is, what is the direction of the force when the magnetic field is reversed? Now let's remove all these marking. Now we are saying that we are reversing the magnetic polarity. So you have the south pole here, you have the north pole here. Use the Fleming's left hand rule again, north to south, the current going this way, the force goes down. So the new force that you get, it goes down. Please do remember, because of the lateral inversion, my finger orientation might not be exactly what you see. What I am doing is not exactly what you see. But you should be using the Fleming's left hand rule correctly, and you should get to see that the force is actually reversed, right? So what do we understand from this particular topic, from these two particular questions here? That whenever the current is reversed, or whenever the magnetic field is reversed, the force is reversed. All right. a little bit of notes for you all to make examination kind of things that we are going to discuss here. So you can take out your textbooks, take out your pens and make some notes. The force is increased. Now the force that you are generating here, the force which is experienced by the wire here, it can be increased if, how can you increase the force? Common sense and logic. If the current is increased, the current in the wire is high, the force is high, right? If you're using stronger magnets, the force experienced is high. And the third way in which you can increase the force is by increasing the length of the wire in the field. How do you increase the length of the wire in the field? You can take this wire, make multiple loops of it like this, and then ultimately it goes back to your battery. So if you see the effective length of the wire, inside has increased 4 times. I've taken the loop 4 times. 1, 2, 3, 4. Effective length of the wire which is inside between the poles of the magnet has gone up 4 times. The force experience will also go up 4 times. Right? Now the next set of points we are going to understand is the direction of the force is reversed. How can you reverse the direction of the force? Think about it, easy for you to understand and answer yourself. The direction of the force is reversed if the direction of the current is reversed, or if the direction of the magnetic field is reversed. So either you reverse the direction of the magnetic field or you reverse the direction of the current, it reverses the direction of the force. Now this is something that we practiced already a while before, right? Okay, so some more important points worth noting. The force is the greatest when the wire is perpendicular to the magnetic field. What does it mean? The force is 0 when the wire is parallel to the field. So what does these 2 points mean? Let's understand it on a whiteboard. I'm taking this to a new screen here. Okay, so let's quickly draw 2 magnets. Right, so you're placing 2 magnets opposite each other. So I'm taking 2 bar magnets like this, and you have to make sure that the opposite ends face each other. Say that this is the north pole of this magnet. So obviously the other end is the south pole. This is the south pole and the north pole. So how do the magnetic field lines in between these magnets look like? Let's draw the magnetic field lines in between this space. That's how the magnetic field lines in between the space looks like. Right, let's put some arrows because magnetic field lines always carry arrows. Right, so let's understand the first point. The force is the greatest. When is the force greatest? When you're holding the wire perpendicular to the magnetic field line. So let's take the wire. So the green thing here, the green line that I'm going to draw here, it's the wire. This is your wire. Right? So when the wire is held perpendicular to the direction of the magnetic field lines, this angle is 90 degrees, but then the force is the maximum. And when the wire is held parallel to the magnetic field lines, the force is 0. Parallel means, let's understand the second point as well. Parallel. So this is the perpendicular scenario. What is a parallel scenario? A parallel wire would look something like this. Let me use the green color only for the wire. This is your wire. This is your parallel wire. When the wire is parallel, the force experienced by it is 0. This is a very, very important concept to understand. Only when the wire is cutting the magnetic field of lines, the force is experienced. Now, at this particular angle, when the wire is parallel to the magnetic field lines, it is not intersecting, it is not cutting the magnetic field lines. Whereas, if the wire is at this particular angle, it is cutting the magnetic field lines. It is cutting the magnetic field lines at this point, this point, this point. Let's take another scenario. The wire like this, it's still cutting, right? It's cutting the magnetic field lines. It is cutting the black lines. The third scenario, perpendicular, which is the best scenario, right? So in all the three scenarios, scenario 1, 2, or 3, when the wire is held in a scenario in a position like 1, 2, or 3, force is experienced because it is cutting the magnetic field lines, right? But the force experienced is the maximum when the wire is held perpendicular 90 degrees, as in scenario 3, perpendicular to the magnetic field lines. This is what these 2 points mean. The force is the greatest. The force is the greatest when the wire is perpendicular to the magnetic field lines, and it is 0 when the wire is parallel to the magnetic field lines. So this is the scenario where it is perpendicular, and this is the scenario where the wire is parallel. 0 force, parallel, perpendicular, the greatest force. Let's understand this experiment, the kicking wire experiment, which lays the foundation for understanding the working of electric motors. It's very important that we understand this experiment. Alright, so let's understand what you see on the screen right now. Right? So easy and simple to understand. You see a magnet, north pole of the magnet and the south pole of the magnet, easy to understand. It is placed on a wooden block, right? And then you see a power supply. And from this power supply, a wire is coming and it is hanging in the space between the magnet, right? There is a switch as well in between, right, to on and off the current in this wire. This wire is hanging in between the poles of the magnet with the help of a cotton thread. Alright, so how does the current flow? Let's mark the flow of the current first. The current always comes out from the positive terminal. So that's how the current is moving all the way, and it moves towards the negative terminal. Say that you have put the switch on. The switch is on. The current is flowing. Think about what is the direction of the force which is experienced by the wire which is in between the poles of the magnet. Use the Fleming's left-hand rule and think about the direction of the current. So let's use the Fleming's left-hand rule. What is the direction of the field? North to south. What is the direction of the current? Down. So what is the direction of the force? Force is outwards. What is the direction of the force? The direction of the force which is experienced is outwards, like this. Ultimately, what you'll see when, as soon as you'll switch on the current here, you'll see that the wire will move. You'll see that the wire will move and it will come out like this. Right? So the wire will not be in this position anymore. It will move, it will curve, and it will move out in this space. When you'll put off the current, when you'll put off the switch, the wire will move back. The wire will move back to its original position. As long as there be a current, the wire will experience an outward force. The wire will experience an outward force and it will move out as I'm depicting with the blue ink. Right? So wire will not be in this position anymore. It will move out. Now let's think a bit more about the scenario. Say that you reverse the current. How can you reverse the current? How can you reverse the current? Say this terminal is the negative terminal, right? And this is your positive terminal, right? So I'm removing this. This is your negative terminal. This is your positive terminal. The current is now flowing this way around. Think about the direction. Work out the direction using the Fleming's left hand rule. Let's take out your left hand. Hold all the first three fingers in perpendicular direction to each other. The field is north to south. The current is moving up. The current is moving up. Which direction is the force experienced? Backward. Right? Now the wire is pushed backward. So how does the wire move? The wire will move to a new position like this. It will move inward, right? So the wire will not be in this position anymore. You'll see that the wire has moved inward. You reverse the direction of the current, the direction of the force experienced also reverses. This is called the kicking wire experiment. Very, very easy to understand. Very, very simple. If you understand the Fleming's left hand rule, if you understand that a conductor which is carrying current and it is placed in a magnetic field, it experiences a force. If you understand these simple concepts, you can easily understand the kicking wire experiment. Now let's talk about something which is actually a little bit more technical but not difficult to understand, believe me. So why the wire moves? Why the wire moves in a particular direction? So Fleming's left hand rule gives us the direction, but why? Why the wire moves out or in, right? Why not the other way around in different scenarios, right? Why a particular direction? Why the movement happens in any particular direction? So let's understand this. Let's focus on this picture, right? You have two magnets. Magnet 1, magnet 2, opposite poles facing each other. The magnetic field line in the space in between would look like straight lines from the north of one magnet going and entering the south of the other magnet, right? So let me take this picture on my whiteboard. So this is your magnet. And another thing that you have is a current carrying wire. Right? This is a wire. This dot with the plus sign indicates that the current carrying wire, the wire is carrying the current downwards. That means the current is moving inside your screen. So the current is moving from outside your screen to the inside of your screen. That's the direction of the movement of the current. Right? Because the current is flowing in this wire, there is a magnetic field around this wire. There is a wire present which is entering your screen at this yellow point, right? There is a magnetic field around this wire, right? So what we have to do now, we have to bring this wire, take this wire and put it inside this magnetic field. Put this wire inside the magnetic, in between the two magnets. What do you see here? Line of forces by the wire, line of forces by the magnets, they are in the same direction. They'll add up. They'll add up. They'll add up where? Above this wire. Whereas below the wire, line of forces by the wire and the line of forces by the magnet, they are in opposite direction. They'll subtract. There is a subtraction happening here. Field by the wire and the field by the magnet, they are getting subtracted, they are getting cancelled, they are cancelling each other out below the wire, whereas above the wire they are adding up. Right? What happens as a result? This is what happens. The combined, this is what happens. The combined magnetic field looks something like this. Above there is addition, so there is a stronger force magnetic field lines of forces present up and weaker magnetic field lines of forces present down. If you see, this is a weaker zone, hardly any magnetic field lines of forces present here, but strong magnetic field lines of forces present here. Strong magnetic field lines of forces, almost no magnetic field lines of forces present here. As a result, the wire is pushed down. As a result, the wire is pushed down. Right? Slightly technical. If you want, you can just rewind this part of the video again to understand it better. This section talks about why the wire moves. It is because of the resultant of the magnetic field which is produced, by the magnet and the magnetic field which is produced by the current carrying wire. On one side the resultant is more, on one side the resultant is less. Right? Movement due to forces always happen from a direction of high force to a direction of less force. So the wire moves down. There is a high force pushing it downward, right? Therefore it moves down. The magnetic field of the magnet and that of the wire cancel each other out on one side of the wire. They cancel each other out on one side and reinforce each other on the other side. So let's understand which are these two zones. They are cancelling each other in this zone and they are reinforcing each other in the upper zone. Here you have strong magnetic field, magnetic force, strong forces. Here at the downward portion, the green box, you have less force present. What happens as a result? The result is that the wire is pushed sideways by the magnet towards the weaker part of the field. As a result, this whole wire, this whole dot that you see where the wire is going inside the screen, this whole wire moves down. The whole wire that you see, it experiences a force and it moves down. Right? You can also use the Flemings left-hand rule to determine the direction of this force. Field north to south, current is moving inside your screen, force experienced downwards. The wire which is carrying the current, experiences a force downwards, it moves down. Right? I hope this part is well understood. If there is any doubts, please post your questions in the comment box. Let's practice a question now on the motor effect. There is a force on the wire in the diagram on the right. So there is a current in the wire which is placed in between the magnets, so it will experience a force. So you have to answer these three questions. If you want, you can pause the video for a minute, answer these questions and come back and play the video again. So three ways in which the force could be increased. You can either increase the current in the wire, use stronger magnets, or you can increase increase the length of the wire by looping this wire multiple number of times around in this space. Use Fleming's left hand rule to work out the direction of the force. I'm talking about question number 2 now. Field north to south, current going inside, force will be up. So what is the direction of the force? In the upward direction. So let's talk about question number 3. 2 ways in which the direction of the force could be reversed. You can either reverse the current or you can reverse the polarity of the magnet. You have to do one of them. You cannot do both of them. If you do both of them, if you reverse the current and reverse the magnet both at the same time, the force will not reverse, right? You have to either reverse the current or you have to reverse the polarity of the magnet to reverse the direction of the force. Alright, so with this, we finish this chapter, and the next video talks about a very, very important application of what we have learned in this chapter to understand the working of the electric motor. So in the next chapter, we'll be talking about electric motors. Thank you so much.